I'm back at you. Another video from Miss Baldwin. This one is on reaction energy. So if you need help with endo and exo and enthalpy and entropy and disorder and all that stuff, even specific heat, you have picked the correct video. All right, reaction energy. All right, first thing, endo and exo, right? One of them releases heat and the other one absorbs heat. Now, which one do you think is going to do which? All right, I'm going to draw a little table for you. One side is going to say endo, and one side is going to say exo. Now, we truncate these words, but what do they mean? Endothermic, therma, meaning heat, all right? And exothermic, all right, also meaning heat. All right, exo means exit, okay? So these are going to produce heat, all right? So they're going to feel hot. All right? Don't joke my handwriting. Miss Baldwin needs help with her handwriting. All right? Endothermic. All right? Endo, inside. It's going to take in heat. It is going to require. That's the word I'm going to use. It is going to require heat, and it's going to feel cold. All right? You feel cold. Why? Because you're getting robbed. That reaction is taking energy from your hand or your face or your body or something, and you feel cold. You feel the heat being taken away from you. So endo is going to feel hot. Exo is going to feel cold. Now we indicate the difference in these two with a little graph, all right? And we have these little, I like to call them hump graphs, these little camel-looking graphs that kind of help us tell. Exothermic, all right, is going to start up high and end down low. Okay, and on this axis is going to be reaction process, and on this one is going to be energy. Energy is going to go up and it's going to come back down. This side is for what it starts, and this side is for where it ends. All right, now all reactions start with reactants, so I'm going to put an R here, and products. Now for exothermic, which has more energy? Can you see it? More energy is in the reactants. The products have less energy. Why? Because they produced it all. They released the energy on you. Okay? So, exothermic is the roller coaster you want to ride. Because that one comes all the way back down to the ground. And I don't know about you, I don't like being stuck on roller coasters. Random. Now, for endothermic, they're going to feel cold. So, they're going to start low and end up high. All right, again, this is our reactants, and these are our products. What has more energy? The products do, because the reactants had to gain energy. They required heat in order for the reaction to take place to produce those products. All right, so that's the difference between endo and exothermic reactions. Any questions about that? Cool. Now, for an endothermic reaction, there's something called enthalpy. Do you see it up here? Look. Enthalpy stands for delta H. That is the amount or the name we give for the heat either produced or the heat released. Now, which one is exo going to do? Is exo going to produce heat or is exo going to release heat? Exo, right, is going to produce heat. So because heat is produced, delta H is going to be a negative. See that? Delta H is going to be a negative number. -5, -2. Negative means produced or released. So the opposite is true for what? Endo. Delta H is going to be positive. All right. Now, on your testing or whatever, you may see, a reaction that looks like this. Let's say we have A plus B making C. All right. What kind of reaction is that? Come on now. What kind of reaction? That's a synthesis. Two things becoming one. Okay. Now you may see something on the right hand side of the reaction that says delta H equals plus 5 kilojoules. See that? Well, delta H is positive. Now, when is delta H positive? Oh, is this the right one? When is delta H positive? Here we go. Delta H is positive for what? Endothermic. So this would be an endothermic reaction. For endothermic reactions, is energy a product or reactant? Is it a product or reactant? Well, Ms. Baldwin just told me that for an endothermic reaction, it is going to endothermic, that's right. Endothermic is going to require heat. Okay? So if endo requires heat, heat is not going to be a product. Heat is going to be a reactant. So on this side, I would put heat. Okay? I know you can't really see it. It'd be heat plus A plus B makes C. Right? Everything else would be the opposite for exo. Exo, this one would be a negative 5 kilojoules. And heat would be on the product side. Because heat would be what? Produced. Do you see that? Heat would be produced. Alright? So that's what enthalpy is. It's a measure of heat. What's the next one? Bum bum bum. Entropy. 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 Do we love entropy? Of course we love entropy. Entropy is disorder. Disorder. That's my little scary voice, like when you're on the movies. Disorder. Chaos. Things going all over the place. Help me. That's my little disorder movie for entropy. All right. Entropy is disorder. Okay. Now, do you think our planet is going towards order or towards disorder? I don't know about you, but I think it's going toward disorder. Every time I clean my room, it's clean for a while, then eventually, naturally, something happens to push it towards disorder. So, here's an example of what you might see with entropy. You might see an equation that says Na, and let's say it's a solid, and it goes to Na that's a liquid. Okay, you see that? It says Na was a solid, and then it went to a liquid. Well, if it went from being a solid to being a liquid, did it go toward disorder? Or is it getting more ordered? It's getting more disordered. Why? Because solids are ordered, liquids aren't as ordered, and gases are all over the place. They're not ordered at all. So this will be an increase in entropy. All right? So delta S, it's going to be a little backwards here, is going to be a negative. All right? Negative means it's kind of going the way nature wants to, and it's going to be expressed. All right? So if it were going from a liquid to a solid, the opposite way, entropy would be positive and it's going toward more order. Okay? So we use entropy. Can y'all see it? Good. We use entropy and enthalpy to be able to tell whether a reaction is spontaneous. All right? If it's going toward disorder and if it's releasing heat, it's pretty much going to be spontaneous. All right? Some things just happen. This last equation, I'm moving on. Bum, bum, bum. Specific heat. Q equals MC delta T. 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 All right? That's our equation for specific heat. We also have a little baby one that says Q equals the mass times the heat of fusion or the heat of vaporization. Real simple. All you got to do is use the formula. Specific heat is, y'all know what that is? Do you know what specific heat is? All right. Normally it's indicated by letter C, right? And it's the amount of energy it takes to heat 1 gram of substance 1 degree Celsius. So if I wanted to take 1 gram of copper and I wanted to heat it up by 1 degree, let's say the copper was at 25 degrees Celsius, which is room temperature, and I want to get it to 26 degrees Celsius. All right, that's 1 degree. That will be the specific heat of copper. Now let's just make up a number. Let's just say the specific heat of copper is 8. All right, it's going to be in a unit called calories per gram degree Celsius or joules per gram degree Celsius. Calories, that sounds familiar, right? Kind of like what we eat, right? So calories and joules are measurements of energy, all right? So the specific heat is how much energy it takes per gram of substance to heat it up per degree. So if I want to heat it up a lot more degrees, it's going to be higher. It's going to take more energy. If I have a lot more copper, say instead of 1 gram I have 10 grams, well, I'm going to need a lot more energy. But if I want to know how much energy, I'm going to start with the specific heat, the amount it takes for 1 gram, and then I would either multiply it or double it or triple it based upon how much copper I have and based upon how much I want to heat it up. All right. So for a specific heat, when I'm trying to calculate that, I need that information. I need to know how much water I have, or how much copper I have, or how much ice I have. See that M? That M means mass. I need to know how much of it I have. Now, the second part, you see that C in the orange equation? That C means what? that means specific heat. All right. Now you should know by now. For water, it's 1 calorie, 1 calorie, 1 calorie, 1 calorie, and for joules is 4.184. 4.184, 4.184, 4.184. All right. So you should know that for water. Now they give you another substance like aluminum or wood or I don't know, iron. They'll probably give you a data table that has their specific heat. So I need to know the mass. I need to know how much do I have. I need to know specific heat, the amount it takes to heat up just a little bit of it 1 degree. Now, delta T stands for the change in temperature, and it's the final temperature minus the initial temperature. So I need to know how much are you going to heat it up. Are you going to heat it up 5 degrees or 2 degrees or 20 degrees? So you got to know that difference in temperature. If you're going to change it per gram per degree Celsius, you got to know how much grams, and you got to know how much you want to change it based upon temperature. Now, for certain processes, we can use this little baby equation. You see it? This is the little baby equation. I'm just a baby. I'm so small. I'm just playing. All right. So this is the baby equation. So this one, we don't need to change the temperature because for these processes, temperature isn't going to change. Here comes the review. For what processes will energy not change? Well, I'm going to draw a little diagram, and hopefully it should stick out to you like a sore thumb. What is that? Huh? That's our heating curve. And there are certain portions of the heating curve where temperature is not changing. We have time and we have temperature. All right, see that? Now, this spot and this spot, temperature and time are not changing. What's happening over those little flat portions? Phase changes. All right, so freezing, freeze, and melting, and then we have vaporization and condensation. Condensation. All right, hopefully you can see that. Freezing and melting for the first little plateau, and then for the second one we have vaporization and condensation. Now those two areas, we're not going to have a delta T. We're not going to have a change in temperature. We're going to use the baby, the little bitty baby equation because those have specific amounts of heat required. Now, when we're talking about freezing and melting, the word we use is fusion. Boom, boom, boom. Can you see it? And when we're talking about vaporization and condensation, we use the word vaporization. Okay? So we have such thing as a vaporization heat or heat of vaporization. And we also have what's called the heat of fusion. All right? So sometimes if I want to just melt a certain amount of ice or if I want to boil a certain amount of water, I don't need the delta T because I know the boiling point of water. I just need to know what is the standard amount it takes to boil water and how much of it, the mass that I have. Say goodbye to the baby. So this has been reaction energy. We talked about endo and exo. Exo feels hot. Endo feels cold. Delta H is enthalpy. Delta S is entropy. And then we got specific heat. All right? Miss Ball was crazy, y'all. I love you. Peace.